Okay, so in this video, we're going to look at the differences between conducting materials and insulating materials and how they respond. There are similarities in them, and there are also differences between them. So one of the things that makes something a conductor, really the main property, whether you're talking about electrical conductivity or you're talking about thermal conductivity, the ability to transfer heat, ultimately what makes both of those things happen is because of something called free electrons. And free electrons in a material are these electrons which are so loosely held onto their atoms that they essentially can leave anytime that they want. Now, most atoms are not like that. Most atoms that are, for example, in your body, they're not conductors. They hold onto their electrons very tightly. Now, they may trade with an atom to form a bond, but they certainly don't just let electrons go away. But metallic objects, and what I mean by metallic objects is not just like a single metallic atom, but I mean a large collection, like a piece of metal. Like, for example, the metal at the tip of this pen, or the metal that might be in like the legs of the table that you're sitting at. Those materials have something called free electrons, and that is these very, very loosely held electrons that are able to migrate around anywhere that they want to go. Now, there's a pretty wide range of conductors when you think about the fact that all metals would be conductors. So copper, gold, silver, iron, all of those are metals. They all contain at least one or more free electrons. Each of those atoms will contain one or more free electrons. And it's those free electrons that are able to conduct electricity, to be able to conduct heat. That's what gives metals there's such special properties. Now, there is another material which is not a metal, and that is graphite. Graphite is pure carbon. Just like diamonds are pure carbon, but in graphite, the atoms are connected together so that the four bonding electrons for carbon, three of them form very strong bonds. And then that fourth electron is just kind of very loosely held on. It's kind of in between layers of the graphite. And that electron is able to move pretty freely, almost as though it was a metal. So it can conduct electricity and also will transfer heat very well. If we drew a picture of what the atom would look like, if I drew a large picture, I'm sorry, not of the atom, but of an object, and just imagine that there were charges in there. So I've drawn equal numbers of positives and negatives to indicate that this object is neutral. But what I would find is that some of these electrons, some of these negatively charged particles are so loosely held that they can freely migrate around and they'll move around. And as they move around, they'll push around their neighbors. So this guy, once this guy moves and leaves and comes over by this atom, well, there's too many electrons here now. So they're going to start to repel each other, and this guy is going to begin to move like this. This guy is going to begin to move like this. And as they do, these guys will just move around in a completely random way. I mean, this is no exaggeration. Any piece of metal that you're looking at has electrons just moving around constantly, just constantly moving from atom to atom as they jostle around, almost like they're at a party, just kind of moving around to different spots and different locations, just never quite settling with any one particular atom. It's almost as though they don't belong to any particular atom, even though they are necessary for that atom to be electrically neutral. Those electrons are not going to leave the metal entirely. It's just that where they are in the metal, their position is just constantly changing. I mean, just literally, they're constantly moving around to different atoms around the outside of the atoms. They don't go through the middle of the atom. They move out along the edges of the atom, along that outer edge of the shell of the atoms. Now, insulators, on the other hand, would be exactly the opposite. These are materials in which charges do not move easily. Now, that doesn't mean that they can't move at all. That just means that it takes a lot to make them move. They don't move easily like metals. Metals conduct electricity very easily. Insulators will conduct electricity, but only under very different conditions than what the conductors will do. And the reason why the charges don't move so easily is because they either do not contain any free electrons or they contain very, very few free electrons. There's a lot of materials that are insulators. I would encourage you to think about them. Maybe pause the video for about 10 or 15 seconds and just think of all the different things that you could think of that you would classify as being an insulating material, meaning that charges don't move very easily through it and heat also does not move very easily through it. Topping the list would be Ben Franklin, one of the first people to do experiments, found one of the materials that was an insulator is rubber. Today, we don't use rubber as much as they did back then, but today plastic has kind of replaced many of the things that rubber might have been used for. Plastic's super common. It's an insulating material, doesn't really have any free electrons. Glass also is a great insulator. This is why we do a lot of experiments in beakers that are made of glass, because they're great insulating materials. They trap the heat and the electricity inside. Wood would be another example. And then the last one I'll put in here is fabric. So cotton, wool, basically any kind of material that is a fabric is generally an insulator. Now, that's not true that all. There are some materials that might be considered to be fabrics that do conduct electricity just a little bit, but in general, most fabrics that you're going to run into in your life, they do not contain free electrons, and so therefore they are not going to be conductors. They will be insulators. Now, the atoms inside of an insulating material looks a little bit different. I'm going to draw this same exact picture that I drew before. Okay, but the difference between an insulator and a conductor is that these guys are bound together very tightly. So the way I'm going to indicate that is to draw a little circle around it to indicate this is one atom with its positive charged protons and its negatively charged electrons, but all of the electrons are tightly bound. They cannot leave. This guy cannot just migrate away and go to wherever he wants. He has to stay here. They are tightly bound. And so while you'll see as we go forward with this topic that there are some things that are still similar, even conductors and insulators can behave in the same way, but there's something slightly different going on inside of them in the way that the way the charges in a conductor move compared to the way the charges in an insulator moves. So conductors and insulators, these are the two kind of ends of the spectrum. And just to really illustrate that for you, let me draw that spectrum down here. Let's imagine a line in which on one end we have pure insulators, and on the other side we have pure conductors. Okay, well, in the pure conductor side, metals are not pure conductors. They're good conductors, but they're not pure conductors. So on this side, we would have things like, for example, copper. Copper is a really good conductor. It's not a pure conductor. Not quite as good a conductor would be something like iron. Gold, on the other hand, is even better than copper as a conductor. And then the only thing that we would really consider to be pure conductors, in order to be a pure conductor, they would have to be something called a superconductor. And this is something that allows charges to move without any restrictions whatsoever. On the other end of the spectrum, we don't have anything called a super insulator. There's just nothing is really called a super insulator. We don't have really a term for that. But on this side, we would have lots of things like, for example, wood. Wood is on the insulating side of the spectrum. Things like glass. Plastic is also a great insulator. Now, what about in the middle? What about things that are not great insulators, but they're also not great conductors? So in this region right here, we refer to these as semiconductors. And we make materials in computers, for example, that contain tons and tons and tons of semiconducting material, and they can conduct under the right circumstances, but they don't always conduct. So they really truly are in that middle ground, not a pure conductor, but also not a pure insulator. So in the next video, we're going to take a look at what happens in terms of conductors versus insulators when you bring charged objects nearby. There's a similarity in the way they behave, but there's also some distinct differences, and we'll explore that in the next video.